Welcome back, everyone. Today, we're going to be diving into something, well, kind of challenging, but super cool.
Calculus.
Yeah, calculus, but don't worry, we're not going to, bore you with formulas and stuff.
Exactly. We're going to focus on the big ideas, derivatives, and gradients, and how they actually help us understand, like, the real world.
Yeah, like how things change and move,
Mhm.
which is, pretty much everything.
Okay, so let's start simple. Derivatives. I remember struggling with those in school. What are they, really?
Well, a derivative tells you how fast something is changing at a specific moment.
Okay. Can you give me, like, a real-world example?
Sure. Think about driving a car.
Yeah.
Your position is changing as time goes by.
Right. Obviously, I'm moving.
Right.
Yeah.
So your position is a function of time, and the derivative of that function that tells you your speed at any given instant.
Oh, I see. So it's not my average speed over the whole trip, but my speed right now.
Exactly. It's like what a cop would see on their radar gun. Instantaneous speed. And that's what the derivative gives you. Gotcha. So how do we actually calculate a derivative? Does it involve, like, graphs and stuff?
It can. Imagine zooming in on a graph of, say, your car's position over time. As you zoom in closer and closer, the curve starts to look straighter.
Right. Like less curvy.
Yeah. And we know how to find the slope of a straight line, right? Rise over run.
Yeah, I remember that from way back.
Well, that slope of the straightened out curve, that represents the derivative at that point, how steep the curve is at that very moment.
So the steeper the curve, the faster I'm going. Makes sense.
Exactly. Now, there's also a more formal way to define a derivative using something called a limit.
Ooh, limits? Sounds complicated.
It's not as bad as it sounds.
Yeah.
Basically, we look at the change in the function's output, like your position, divided by the change in the input, like time.
Okay, so change in position over change in time. Sounds kind of familiar.
Right. And then we see what happens as that change in the input gets super tiny, almost zero. That's the limit part.
Ah, so we're taking the average speed over a tiny, tiny interval and shrinking that interval down to nothing. Boom, instantaneous speed.
You got it. And the cool thing is, you can find the derivative of all sorts of functions, not just those describing motion. Anytime you want to know how one thing changes in relation to another, derivatives are your friend.
This is making more sense now. But I know we got to level up, right? We talked about gradients earlier. How do those fit in?
Gradients, well, they're like derivatives, but on steroids.
On steroids? You've got my attention.
Think about hiking up a mountain. The height of the mountain at any point depends on, well, where you are, right? Like your north-south position and east-west position.
Right, two directions.
Exactly. So the height is a function of two variables. It's like a 3D graph. And gradients come in when we have these multivariable functions.
Okay, so it's more complex because we're dealing with more than one input.
Exactly. Now, imagine you want to find the steepest path up that mountain. You need to know how the height changes, not just in one direction, but in both the north-south and east-west directions at the same time.
Whoa. Okay, things are getting tricky now.
This is where partial derivatives come in.
Partial derivatives, another new term.
Think of it like this. We're going to look at how the height changes with respect to each variable separately.
Okay, so like holding one direction constant while we see how the height changes in the other.
Exactly. And once we have these partial derivatives, we combine them into the supervector that's the gradient.
A supervector. What's so super about it?
It points in the direction of the greatest increase.
So in our mountain example, the gradient is pointing straight up the steepest slope.
You got it.
Now.
And the longer that vector is, the steeper the slope. Pretty neat, huh?
Wow, the gradient is like a super compass.
Exactly. And this idea isn't limited to mountains. Think about a weather map.
Like those ones with all the different colors for temperatures?
Yeah, exactly. The gradient at each point would point towards the hottest spot nearby.
Whoa, so if you follow the gradient on a weather map, you'd be walking towards warmer and warmer temperatures.
You got it. And these gradients aren't just for mountains and maps. They pop up everywhere.
I'm starting to see that. So we've got derivatives telling us about change at a specific point, and gradients showing us the direction of greatest change in multidimensional spaces.
That's a great summary. And we'll delve into some real-world applications in the next part of our deep dive.
Can't wait. This is already making me think about calculus in a whole new way. Okay, so gradients are like super compasses. I'm ready to see where they lead us in the real world.
All right. Well, you might be surprised to hear that gradients are like super important in machine learning.
Machine learning. I mean, I know it's a big deal, but I always thought it was mostly, stats and data and stuff.
Oh, stats and data are definitely important, but calculus plays a big role too, especially gradients.
Really? I never made that connection. How
Yeah.
so?
Let's say you're building a machine learning model, right? Like one that predicts house prices.
Okay, yeah.
You have all this data about houses, square footage, bedrooms, location, the whole shebang. And you want the model to, learn from that data and then predict the price of a new house accurately.
Right, so it has to figure out how all those features, like square footage and stuff, relate to the price.
Exactly. And that relationship is often represented by, like, a mathematical function.
Okay, a function.
Yeah. And the model has to find the best possible parameters for that function, the numbers that make it predict the prices really well.
So it's like fine-tuning a machine to get the output you want.
Yeah, exactly. And that's where gradients come in.
Okay, how do they fit into all of this?
So think of the model's parameters as like coordinates in a multidimensional space.
Multi-dimensional space. Sounds kind of abstract.
It is, a bit. But each combination of parameters is like a point in that space, right? And at each point, we can calculate something called a cost function.
A cost function. What's that?
It basically tells us how well the model is doing with those specific parameter settings.
So lower cost means the model is predicting prices more accurately.
You got it. And the goal is to find the parameter settings that minimize the cost, make it as low as possible.
Okay, and how do we do that?
That's where gradients come in. They're like our trusty guides.
All right, I'm ready for the guidance.
The gradient of that cost function tells us which way the cost increases the fastest.
So we want to go the opposite way then.
Exactly. We want to go in the direction of steepest descent to get to the lowest point on that cost function landscape.
I get it. It's like we're using the gradient to navigate down a mountain, trying to find the lowest valley.
Exactly. And there's this whole technique called gradient descent that a lot of machine learning algorithms use. It basically takes small steps in the direction opposite the gradient until it finds the minimum point.
So it's using the gradient to, like, iteratively improve the model.
You got it. And the amazing thing is that this works even in like super high dimensional spaces where we can't even picture what's going on.
The gradient always points the way. I'm starting to see why you said gradients are on steroids.
Right. They're super powerful. And this is just one example. Gradients are used in image processing, robotics, physics simulations, you name it.
Wow, okay. You've convinced me. Gradients are awesome. But before we move on, can we go back to partial derivatives for a second?
Yeah.
I want to make sure I really get how they work.
Sure thing. It's always good to nail down the basics. So let's say we have a function that describes the temperature at a point on a metal plate.
A metal plate. Okay, I can picture that.
That temperature could depend on, where on the plate you are. Let's say we use x and y coordinates.
Okay, so the temperature is a function of two variables, x and y.
Right. Now, let's say we want to know how the temperature changes as we move along the x direction.
So like horizontally across the plate.
Exactly.
Yeah.
We need to keep the coordinate constant like we're slicing the plate along a horizontal line.
Okay, I'm visualizing it.
Then we take the derivative of the temperature function with respect to x. That's the partial derivative with respect to x.
So it tells us how much the temperature is changing as we move along that horizontal line?
Exactly. It's like the slope of the temperature curve along that line. And we can do the same thing for the y direction, holding x constant and taking the derivative with respect to y.
Right, so we get the partial derivative with respect to y.
You got it. And then the gradient combines those two partial derivatives into a vector.
And that vector tells us the direction of greatest increase in temperature on the plate.
Precisely. The gradient is like a compass pointing towards the hottest spot.
This is making so much more sense now. So partial derivatives break down the change into its components along each variable, and the gradient combines them to show us the overall direction of greatest change.
You nailed it. That's the power of the gradient. It captures how things change in a multidimensional world. Pretty cool, huh?
It really is. You've definitely made gradients less mysterious for me. What else have you got for us?
Okay, so we've climbed derivative mountains and followed gradient compasses. What else is there to explore in this calculus world? Well, I want to circle back to something you said earlier about derivatives. You know how they give us that instantaneous speed, like zooming in on a tiny moment in time?
Yeah, it's like a snapshot of the car's motion.
Right. Now, what if we took that zooming in idea and applied it to those multivariable functions, not zooming in on time, but on a tiny region of the input space, shrinking it down, down, down?
Okay, I'm picturing like a little square or a cube around a point getting smaller and smaller.
Exactly. As we zoom in, the function starts to simplify in that region. It might become almost like a straight line or maybe a parabola, depending on the function.
So we're approximating the function's behavior with a simpler shape near that point.
You got it. And the simpler shapes are way easier to work with mathematically.
I bet. But how does this zooming in actually help us solve real problems?
Good question. Well, one big application is in optimization. Like, let's say you're designing an airplane wing,
Okay, sleek airplane wing, I'm picturing it.
and you want to find the shape that minimizes drag, right? Make it as aerodynamic as possible.
So we have a function that describes the drag based on the wing's shape.
Right. But that function could be super complex with tons of peaks and valleys, like a
Yeah.
crazy mountain range in multidimensional space.
Yikes, that sounds tough to navigate.
It can be. Finding the absolute best shape, the one with the absolute least drag, can be a real challenge. But that's where the zooming in idea comes in handy.
I'm intrigued. How so?
We can start with, say, an initial guess for the wing shape.
Okay, a starting point.
Right, and then we zoom in on the function's behavior near that point. If we zoom in enough, the function might start to look like, say, a smooth bowl with a clear minimum.
So we've simplified the problem by focusing on a smaller region where the function behaves more nicely.
Precisely. And then we can use our gradient descent friend to find that minimum in the zoomed in region. It's like finding the lowest point in that bowl.
Okay, and I guess we can keep repeating this zoom in, find a minimum, zoom in again, until we get to the overall best shape for the wing.
Exactly. And that's just one example. This idea of using derivatives, gradients, and these local approximations is everywhere. Engineering, physics, economics, you name it.
Wow, I never realized how powerful these calculus concepts are.
Yeah.
It's amazing how they connect to so many real-world problems.
That's the beauty of it. And that's what we've been trying to show you today, how calculus, even though it might seem kind of abstract at first, can actually help us understand and solve really cool practical problems.
Absolutely. You've definitely opened my eyes to the magic of calculus. So to all our listeners out there, remember, derivatives, gradients, they're not just equations in a textbook. They're tools for understanding the world around us, from airplane wings to machine learning models and everything in between.
Keep exploring, keep asking questions, and who knows, maybe you'll discover some amazing applications of calculus yourself.
Couldn't have said it better myself. Until next time, keep those brains buzzing.